Hello. Good morning and welcome to our second plenary session. As president of the Geochemical Society, it's my pleasure to begin today's session by presenting the Society's medals, which recognize some of the most outstanding scientists in our field. However, before starting the ceremony, I'd like to spend a few minutes today to pay tribute to a longtime GS member who passed away only about 2 weeks ago, Professor Jerry Wasserberg of Caltech. Professor Wasserberg was one of the most influential geochemists of the 20th century and even the early 21st century. His studies of meteoritic, lunar, and terrestrial samples were primordial to our understanding of nucleosynthesis and the formation of the solar system. He also contributed greatly to our knowledge of Earth evolution over time and even of the chemistry of the oceans. Jerry Wasserberg was the recipient of numerous awards and honors throughout his very long career. And that included, of course, the Goldschmidt Medal in 1978. Last December, he made a very generous gift to the Geochemical Society, which was aimed at enhancing the prominence of this award by allowing recipients to attend the conference as guests of the Society. Jerry believed it was very important for geochemists to know their history, and particularly to remember the life and pioneering work of Victor Goldschmidt. Today, we also take this moment to remember Jerry's own very many contributions to the Society and to geochemistry as a whole. Okay, now we will begin our presentations with the F.W. Clark Award, which is given to an early career scientist for a single outstanding contribution to geochemistry or cosmochemistry. This could be published either as a single paper or as a series of papers on a given topic. This medal is named for Frank Wigglesworth Clark, who was both a mineralogist and a chemist who lived from 1847 to 1931, and who is often credited with determining the chemical composition of the Earth's crust. This year, the medal is presented to Lawrence Young, Assistant Professor of Earth Science at Rice University. Professor Young is recognized for his experimental and theoretical studies of clumped isotopes and their applications to natural systems. So please join me in congratulating Professor Young on receiving the 2016 F.W. Clark Award. Congratulations. Congratulations, Lawrence. And I wanted to remind you all that Lawrence will be giving a talk today at 1:45 in room 313, so you don't want to miss that. Our next award is the Clair C. Patterson Award, which recognizes an innovative breakthrough of fundamental significance in environmental geochemistry, particularly those which serve society, and which consist of either a single outstanding contribution or a short series of paper that's been published within the last decade. Clair Patterson had a remarkable career, during which he developed the uranium-lead dating method. Using lead and uranium isotopic data from the Canyon Diablo meteorite, he calculated an age for the Earth of 4.55 billion years. And this figure was more accurate than those that existed at the time, far more accurate, and which has remained unchanged for over 50 years. Clair Patterson also played a major role in raising awareness of the dangers of lead contamination in the environment. This year's recipient of the medal named in his honor is William Casey, a professor at the University of California, Davis. Professor Casey is recognized for research addressing environmental chemistry topics, particularly the development of nuclear magnetic resonance technology, which has opened the door for many fundamental studies in environmental geochemistry. Let's give a round of applause to Bill Casey for receiving the 2016 Clair Patterson Award. Finally, we come to the Geochemical Society's highest honor, which is named for Victor Moritz Goldschmidt, who's often considered to be the founder of our field. Goldschmidt's studies of crystal chemistry and his classification of the behavior of the elements in the earth and meteorites laid the basis of modern geochemistry. This year's recipient of the award is Alexander Navratsky, interdisciplinary professor of ceramic, earth, and environmental materials chemistry at the University of California, Davis again. Professor Navratsky is a particularly appropriate choice for this award, since her work has been largely inspired by that of Victor Goldschmidt, as she so gracefully acknowledged in her medal lecture yesterday. Professor Navratsky is recognized for a broad and prolific career that has advanced our understanding of the energetics of Earth materials, specifically the fundamental thermodynamic basis of material behavior and its applications to a wide range of problems in the geosciences. An experimentalist with a specialty in high-temperature calorimetry, she's also exploited a diverse range of other experimental as well as theoretical techniques to understand the structure, property, and process relationships in minerals and related materials. Please join me in congratulating Professor Navratsky as she receives the 2016 VM Goldschmidt Award. Thank you all for your attention. I would now like to introduce Professor Hodaka Kawahata, the past president of the Geochemical Society of Japan, who will introduce our plenary speaker.
I'm Hodaka Kawahata, the past president of the Geochemical Society of Japan. Our community is very happy to host the Goldschmidt Conference this year under collaboration with the Geochemical Society and the European Association of Geochemistry. Please have a fruitful scientific discussions, also the sightseeing at Yokohama. I would like to start today's plenary sessions. I would like to introduce Professor Terry Planck. She is Arthur D. Stoke Memorial Professor, Lamont Doherty Earth Observatory, Columbia University. She has been studying magmas associated with the plate tectonic cycles at both divergent and convergent plate margins. This includes the magma's generations and the cluster recycling. She studied at Dartmouth College and got a PhD at the Columbia University, and has worked at University of Kansas, Boston University, and Columbia Universities. She is a fellow of American Academy of Arts and Sciences and a fellow of the Geochemical Society and others. She has been published over 80 articles in the international journals, and the total citation is approximately 10,000 at the moment. Today, she will give a talk on the topic of volatile input to the volcanoes and eruptions. And please start.
Thank you, Professor Kawahata and President Reisberg, and whoever chose me for this amazing honor, and mostly all of you for being here. This is quite a remarkable opportunity to talk about work that we've been doing at Lamont and with my colleagues at Carnegie and Rice. Don't worry, only the first slide is cut off, but it's an important word, the volatile input to volcanoes and eruptions. So we'll start with a question: How many volcanoes do you think are erupting right now? 15? Someone read my abstract. That was like last year. You know, every week there's about 15 or 25 volcanoes in a state of eruption or unrest. So the answer for last week is 22. And most of these, not surprisingly, occur at convergent boundaries, at arcs, subduction zones. And for that reason, most of them are erupting hydrous basalt to andesitic magma. This is the common magma that's erupting every day. We shouldn't forget, even though it's kind of a rainy day, we're here at Yokohama, we're at an arc, and those of us who are lucky enough to be here Sunday morning actually saw Fujisan, which is a volcano that's not erupting this week, but has erupted hydrous basalt and andesitic magma in its past. This is Pavlov volcano in the Aleutians. It also is not erupting this week, but it did a few months ago. Produced a fairly dramatic ash column that went up about 10 kilometers, 30,000 feet in airspace. Not very many people live on the Alaska Peninsula, but 10,000 people a day fly over airspace in Alaska, where there are 35 historically erupting volcanoes and several that are erupting every year. And Pavlov erupts basaltic andesite. So this is the common magma that erupts, and yet it's not the magma that we think of most or even understand the most about when it comes to eruption behavior or style. And I really like this figure that Helga Gonnerman and Michael Manga put together, because it's one of the few figures that tries to put eruptions in a single context, to look at the whole spectrum of magma types and at the whole range of mass discharge rates, which is what scales to eruption intensity and style, but then tries to document these different behaviors that volcanoes undergo. So at the left side of this diagram, where basalts would plot at low viscosity, you see going from low to high mass discharge rate, volcanoes like Kilauea might transition from Strombolian to Hawaiian eruptive behavior. Silicic magmas plot on the right side of the diagram, and they may transition from domes to subplinian to plinian eruptions like Mount St. Helens has. And this is kind of the way we think of eruptions, often basaltic end members and basaltic eruptions and silicic eruptions. And yet what I just told you is most of what erupts every day is in the middle part of this diagram. The intermediate magmas, in the empty middle of this diagram, they have intermediate viscosities, but the viscosities probably vary as they exsolve water and crystallize, their viscosity will rise. And they erupt in also the same variety of styles as on this diagram, over orders of magnitude difference in mass discharge rate. So here are two arc volcanoes. This is Anak Krakatoa, Fuego, showing Strombolian and subplinian eruption styles. Colloquially, these are known by their volcanic explosivity index, which has a lot of things in it. The plume height and the volume and the discharge rate feeds into this and actually correlates quite well with the VEI. But this is meant to be an order of magnitude scale, and so there's 3 orders of magnitude in eruptive behavior between these two volcanoes on these different days. And this is the question that I want to ask, is why? What controls the differences in a Strombolian and a subplinian eruption in these hydrous basaltic to basaltic andesite magmas? We like to think it has something to do with volatiles. Is this magma wetter than that one? And we'd like to think of this as the same process that happens in the soda bottle, where when the cap is on, the gas, which in the soda bottle is CO2, is dissolved in the liquid under pressure. And we take the pressure off, solubility drops dramatically, the CO2 exsolves into bubbles and rises and fragments the liquid and causes an eruption. We like to think volcanoes behave this very similar way. These arc volcanoes, the predominant gas is water, but the same thing happens. We take the cap off or decompress it, the water exsolves into bubbles and fuels ultimately the buoyancy, the ascent, and the eruption. This is probably true. And so it seems obvious that volatiles, different amounts of volatiles, would drive different eruptive behavior. And this is something we ought to be able to test. And what I want to show in this first part of the talk is that kind of test that really has only been available in the last few years when we've had enough data to test this. So it seems straightforward, but it's really not. What we need to do is find out how much water magmas contain before they erupt, and does that relate to eruptive vigor? And what we have to work with are these, rocks full of holes. And so the evidence that we have is absent. And it's been difficult, and it still is difficult, to estimate how much water was dissolved in magmas before they erupt, how much CO2 is in the seltzer bottle before you open the cap. The main way that we've developed as a community is looking at melt inclusions, little bits of melt that haven't degassed, we hope. So how this works is if we consider magma that starts with maybe 1,000 parts per million CO2 and 4% water at depth, so we're at pressure and depth in the earth, as magmas rise, the solubility drops dramatically for CO2, and so the CO2 that's dissolved in the melt here exsolves into bubbles and vapor, and by the time the magma erupts, there's nothing left in the melt, it's all in the bubbles. Water does the same thing, but it actually doesn't change that much while it's largely undersaturated. Some exsolves into a vapor, but the water doesn't drop until it reaches a depth or pressure near water vapor saturation, and then again, the water exsolves into a bubble, and by the time it erupts, there's essentially nothing left but a rock full of holes. So CO2 is very challenging to figure out how much CO2 the magma might originally have contained, but you can see there's an opportunity. If we had a way to get the magma down here and collect it, we have an opportunity to measure the pre-eruptive volatile content of an eruption. And what we hope then is that melt inclusions, which are little aliquots of melt that are trapped inside crystals, this is showing olivine, that they are kept under pressure and kept from exsolving their vapor and kept from leaking, and that the melt inclusions still contain, and they form down here before the magma extensively degassed. It's a lot of ifs, and that tells us what the pre-eruptive volatile content, at least water content, of the magma is. So this has been a big inquiry of study, and I've worked extensively with Eric Howry. He's been one of the developers of one of the main techniques by ion microprobe and by nanosims to measure the melt inclusions now that they're quenched into a glass and we can polish into them and analyze them by ion probe and measure 5 volatile species, water, CO2, sulfur, chlorine, and fluorine. And with electron probe and laser ablation, ICP-MS, we can measure major elements and trace elements, and something as small as, that's actually a big melt inclusion, something as small as 30 or 40 microns. So this is what melt inclusion data might look like. This is for a single deposit from Seguam Volcano. I see Brad Singer here, he went out there with me, thank you, to collect this amazing sample, this scoria, from actually a VEI-1 eruption, a low energy eruption. Each one of these is a melt inclusion trapped inside olivine, which we look at olivine because it's generally the first crystal to form in a hydrous basaltic magma, and therefore may capture the melt before it degasses. And we see what I just described before, that the CO2 drops dramatically before the water changes much, and then the water drops dramatically once it reaches a point near water vapor saturation. And so even the melt inclusions, which we had hoped capture the magmas before they degassed, have still mostly tracked the degassing path. However, we really hope that we can backtrack to where it all started. And in this case, we would argue that this magma had around 3.5% water pre-eruptively. That's the volatile fuel it had before its eruption. And that's one data point. That's one volcano and one eruption. In 2000, this is kind of how much data existed. Now at the Goldschmidt conference, there are multiple sessions on melt inclusions, but in 2000, it was Tom Sisson and Kurt Rogensack and Alex Sobolev and Fred Anderson had been working on this for a long time. A few people had been developing the ion probe and FTIR techniques, and there was some data. This is mostly 3 cones around Shasta in California, and this is Cerro Negro and Fuego volcanoes in Central America. These are pretty much the only data we had for the pre-eruptive water contents of basaltic to basaltic andesite eruptions in olivine. And then in 2013, when we wrote a review on this, there's kind of been an explosion of data. This is about 60 volcanoes from 7 arcs, 20 studies, 10 or 12 PhD theses, a lot more data. And we find what we always imagined, which is that arc magmas have more water than mid-ocean ridge basalt, so that's a relief. They generally have pre-eruptively, again, this would be the maximum water recorded in a melt inclusion suite, so in a population of melt inclusions, this would be one volcano. With multiple melt inclusions, this would be the highest water concentration. And we see that the values range from about 2 to 6 weight%. And it's not apparent here, but if you took the average on this diagram, it's remarkably similar in every arc, around 4 weight%. And this was not expected. We went to Tonga, which is the fastest subduction zone, erupts bonanites, and we found 4% water. Paul Wallace worked on Mexico. It's a hot slab, flat slabs, continental crust, 4% water. If you look at this on a histogram, it might not have been apparent from the scatter on the previous diagram, but these are the individual volcanoes. There is a real peak here. There's a real peak at around 4% water. And it is a little bit disappointing to measure these melt inclusions, which are a lot of work to find and collect and analyze, and they all seem to have 3-something or 4-something% water. We wrote a paper on this a few years ago with that very question: why do arc magmas contain 4% water on average? I'm not going to tell you the answer. You have to go read the paper. This also isn't an answer. We present 2 ideas: that the mantle has a negative feedback that produces a similar product, that 4% water comes out of the mantle, or that magmas stall in the crust and 4% is reflected in where they stall and where the melt inclusions reset. But I'm showing this slide in part to point out some of the great people who've worked with me on this: Katie Kelly, Mindy Zimmer, Eric Howry, again a collaborator, and Paul Wallace, who's not a collaborator, but a great colleague and who's worked in parallel on this problem. Okay, so wherever there's 4% water, it doesn't matter. It's still very bad news for the eruption problem. How do we explain orders of magnitude variation in eruptive vigor from magmas that have nearly very narrow range of water concentrations? And we could try to make a plot, and I'll show you a plot, of water concentration versus VEI, the explosivity index, but recognize for various reasons that most of the samples that have been studied here were not from known eruptions, and there's reasons for that. But we've looked at several now in the Aleutians in Central America that are from historic and known eruptions where we know the VEI, and that's what this plot would be: water in the pre-eruptive magma, the same water, versus the volcanic explosivity index. So we looked at Seguam before. That was the example I showed you with 3.5 water. It's a VEI 1. It has nearly the same water as Akutan, which is a VEI 5, and made a considerable caldera. Cerro Negro, very high water concentrations, a little above 5%. Shishaldin, almost the lowest in an arc, around 2%, both VEI 3. I'm a deep looker for correlations, and there's nothing here. So no obvious relationships between eruptive intensity and pre-eruptive water. We clearly need more data, but I would say so. There doesn't seem to be a very strong relationship with the total volatile fuel, how much water exists prior to the eruption, and the intensity of the eruption. This really doesn't look like it matters. So what matters? And so we can think of the seltzer bottle again. If I took a seltzer bottle and shook it up and I handed it to you and told you to open the cap and not let it erupt, what would you do? You'd open it slowly. Okay, so there's clearly a rate term, and maybe the rate term is the most important thing. By rate term, I'm talking about the rate at which we decompress the system. So in the seltzer bottle, it's how fast we're opening in the cap. In a magma, it's how rapidly it rises, because pressure's just dependent on how much crust or magma is above that point. And so as it rises, it decompresses. So how rapidly it's doing that, by analogy, may be the important thing. Because there's a lot of things that can happen as a consequence of decompression. So I'm going to kind of use these interchangeably. Magma rise rate, ascent rate, decompression rate, they're not synonymous, but I'll probably use them somewhat synonymously. And my laser pointer's died, if there's another one. Here we go. One of the main ways that we can imagine that the decompression rate or the ascent rate matters is how it enables the bubble and the liquid to segregate and coalesce. So at a low ascent rate, as magma's rising slowly, the bubbles have time to coalesce and rise ahead of the magma, and it could erupt degassed. The rapid rise rate carries the bubbles with it. That's one obvious thing that has even a relationship to the seltzer bottle. The rise rate could also be so rapid that the magma is supersaturated and then nucleates at high nucleation density, and we get many nucleation bubbles that could cause a small fragmentation size and eruption of ash and a plume. There also could be shear heating along the walls for rapid ascent rates that heats and then enables the magma to move yet faster. So they're feedbacks also. They're also phenomena that involve crystals and microlights, and that involve brittle versus not brittle behavior. There's a lot of things that magma decompression rate can affect in the physics of magma ascent. And this is a common notion in our heads too. Marie Edmonds made this very beautiful summary figure of this, looking at magma ascent rates or decompression rates, and correlating that with how much the melt and vapor can segregate. That was my number one on the previous slide. And that this does relate directly to what we see in the vigor of the eruption. Well, there's no actual numbers on this diagram, so maybe that would be useful. And so that's what I want to talk about next, is how do we put numbers on this diagram? How do we measure decompression rates? What are the clocks we can use? And how fast do the clocks have to work? So in the time that it's going to take me to describe this slide, which will be a minute or two, the magma under Mount St. Helens ascended in 1980 from 7 kilometers depth, a few minutes. Water can diffuse along measurable distances in that same amount of time. Okay, that's where I'm going with this. So to kind of rationalize that scale of timing, you can start at the bottom of the diagram and just, again, think of the mass eruption rate or the mass discharge rate, which relates to VEI as we've described. So we have kilograms per second of magma coming out. We can relate that to what comes up the conduit to feed that output rate. If we know the conduit radius, we don't, but let's just say it's around 10 meters. And then we can relate that to the ascent rate if we know the density, which is complicated, but we'll assume something, and then we have to know from what depth it comes in order to figure out how much time it takes to ascend. And that's, you can see on the time scale of minutes to days to months. But the most explosive events here, the VEI 1 to 5 that we're thinking about, are going to be in the minutes to a day time scale. That's a fast clock, and there aren't that many clocks available to us that work at this time scale. However, one involves the diffusion of the volatile species themselves. So how handy is that? The very thing that you want to understand, which is how the volatiles are getting through the melt and into a bubble, are actually moving and diffusing at timescales that are relevant to the decompression process. So this shows for a 50 to 500 micron length scale, just looking at a length scale that we could measure by SIMS or nanosims or FTIR, at magmatic temperatures, how fast does water, CO2, fluorine, chlorine, sulfur diffuse in basaltic liquids? And they diffuse over these length scales on the time scales of, you can see, minutes to hours to days. And so that's useful. Useful clock. What do we measure these in then? So we're going to look at them in melt embayments, I'll call them. They're tubes. You can think of them as tubes or open melt inclusions, inclusions that didn't close. So here's the olivine grain, and here's a melt embayment. It actually is connected to a vapor bubble in the exterior. And at depth, the embayment we're going to assume is hanging out and in equilibrium with the melt around it. So it has the same volatile concentration as the melt around it. Then the system starts decompressing. We want to know how long that takes. As it decompresses, the exterior melt, then the solubility drops of all the volatile species. They exsolve into bubbles. But the embayment, unless it has a bubble in it, can't get the volatile species to the bubble without diffusing it along the length of the tube. And that's the process that we hope to catch and then use as a clock. We did not come up with this. Fred Anderson did, as far as I know, in this nice paper by Liu et al. And then Madeline Humphreys and the group at Bristol applied this beautifully to Mount St. Helens. So what we brought to it is looking at the resolution of the nanosims, again with Eric Howry, and 5 volatile species simultaneously. So again, this is how it might work. This would be along the melt embayment. From the inside to the outside, initially it might have 4% water, like the exterior magma. As the system ascends and decompresses, the exterior vesiculates and has a lower water concentration at the outside. We continue to ascend. It loses the melt loses water to bubbles as it's ascending, and the embayment's trying to keep up with that, dependent on how fast water, in this case, can diffuse. If we decided to stop here after 7 minutes, then the embayment would now equilibrate and have a chance to catch up and have 2.5% water. But if we keep ascending, then we develop these dramatic profiles that we hopefully could measure and then say, oh, this took 9 minutes to ascend from 10 kilometers depth. And that's not far off the example I'm going to show you. So here's an olivine crystal, here's an embayment, a glass tube. There's the exterior bubble that the volatiles are trying to diffuse, diffuse along, to equilibrate with. And then these are the nanosims spots along the embayment, and we're looking at 5 volatile species. We're going to look at samples from an eruption of Fuego, which I've already shown a picture of. It was kind of our VEI4 eruption, a subplinian eruption where we've actually looked at the melt inclusions in great detail, so we know what the closed inclusions are doing that presumably haven't communicated with the exterior. And we were able to find 4 embayments. It's hard enough to find melt inclusions that are big and glassy and don't have crystals and haven't cracked or communicated. The embayments are tough. We want them to be kind of one-dimensional. We want to see a bubble at the outlet so we know where the volatiles are going. We don't want to be crystalline. We don't want to bubble inside it. This enabled us to have 4 samples. We're going to look at the concentrations along this long one. And so that's what this is, from the interior to the exterior of that tube for water and sulfur. First, the blue bars are actually what the melt inclusions in the same sample have. So they have, again, up to 4% water, 3 to 4, and they're uniformly higher than we've measured at the inside of the embayment, which is only around 2.5. So we know the inside of the embayment has dropped, has leaked. Sulfur, on the other hand, is quite high. It's as high as the highest melt inclusion. So we're going to assume that the interior of the embayment is the initial for sulfur. And so only this part has a diffusive profile, whereas the entire water profile has been affected by diffusion to its interior. The curves are model calculations, what the diffusion profile would look like in a forward way for those decompression rates, so 0.3 megapascals per second. This is a fully numerical model because all the diffusivities actually depend on water concentration itself. So the diffusivity is not constant, and the exterior is dropping, obviously, so the exterior boundary condition is not fixed. It's moving at a rate. That's what we're trying to test. And so Philip Ruprecht was very helpful in developing the numerical model for this, and you can see that 1.28 is too fast, and 0.08 is too slow, and 0.32 is just right for both water and sulfur. So that's a good fit. It's a joint solution. It's non-trivial because water and sulfur have order of magnitude or so different diffusivity and different solubility, so that's a good joint solution. All 4 embayments gave us similar solutions from 0.32 to 0.45 megapascals per second, and that's on the order of 10 meters per second ascent. And that's about 10 minutes coming from 7 kilometers depth to fuel this eruption. You can read about this in Alex Lloyd's paper, who's a graduate student, now postdoc at Lamont. That's Fuego. We've started now looking at other eruptions. And so here's the same Fuego profile I showed you. That's the Fuego eruption. And then here's for Seguam. Here's the Seguam eruption. You can see Seguam, which actually starts with similar water, 3.5 to 4, like almost everything, has dropped much more in the interior, and we would say that it decompressed at a lower rate and had more time to lose water on the way to the surface. So VEI4 eruption, high decompression rate, VEI1, low decompression rate. Well, that's going in the right direction. And I hesitate to make this plot. It has 5 data points. It's kind of one of these where you quit when you're ahead. But here's Fuego, here's Seguam that I just showed you. So a relationship between decompression rate and VEI. And then I've also put on here Kilauea, which we've been working on independently. This is not an arc volcano. It's not particularly wet. Actually, these 2 units have similar water concentrations in CO2 as far as we can tell. This is the famous fire fountain, episode 1 of Kilauea Iki. This is the Kanakakoi, which actually was a subplinian eruption that spread ash all over Hawaii, reminding us that Hawaii has erupted in different ways in the prehistoric time. And this is David Ferguson's work that's hopefully will come out soon, and he sees quite a dramatic difference in decompression rate between these 2 different eruptions of Kilauea. And there is Madeline Humphrey's Mount St. Helens point. So there are 5 data points so far with the embayment method, and there is a striking relationship between the explosivity of the eruption and the decompression rate. We could also look, because the VEI scales with something, the VEI is a useful idea, but it's not very quantitative. It scales quantitatively to, well, the decompression rate looks like it's scaling also to the mass eruption rate. So this is how rapidly material mass comes out of the ground. We still see a positive relationship between the 2, now almost the same kind of log-log relationship. And these lines are what one would calculate, actually, for a conduit of a certain size. If you know the discharge rate and you know the decompression rate, they're really only related by the conduit dimension, provided no friction on the walls and other complicating things. These lines actually do include friction on the walls for different magma viscosity. These are our conduit calculations that Helga Gonnerman performed. And what you can see is that these kind of 2 orders of magnitude of eruption potential can all be explained by something on the order of a 7-meter conduit. Mount St. Helens probably is on a higher viscosity curve. It might be a 10 or 15-meter conduit. But that's the first kind of interesting result. Not only does the decompression rate scale with eruptive vigor, but we can use it to get at what the dimensions of the conduit are, which is something that's virtually impossible to obtain but necessary in any quantitative model for how eruptions proceed. And why are conduits 7 to 12 meters? It's an interesting result. So this is something we clearly would like to expand upon, looking at other ways to quantify the decompression rate. These are all using this embayment method, which the embayments are very hard to find. So in the last segment of the talk here, I want to show you work that we've been doing trying to develop another ascent rate meter, a decompression rate meter, using the mineral clinopyroxene. So this is the same diagram I showed before with volatile species, diffusivities, and melt. This is how fast water diffuses through CPX. And while the length of these lines is fairly large, it's because we were looking at an order of magnitude length scale. This line is larger because there really is a huge 4 order of magnitude uncertainty on what the diffusivity of water in CPX. So this is the first thing to address. If we want to use this as a rate meter, we need to understand a little better what's controlling the diffusivity. And Elizabeth Ferris has been working on this for a couple years, and she has some very nice papers. One just came out this month looking at diffusion of water in pyroxene. And this is the problem. Elizabeth reproduced this in our lab, that we can take one diopside, the Jaipur diopside, you can take another, the Kunlun diopside. These are both gem quality diopsides. And this is an Arrhenius plot looking at temperature versus the diffusivity for hydrogen through pyroxene. And these are 3 orders of magnitude different for diopsides. This is the problem that we need to solve. And Elizabeth reproduced work that had been done previously on this. So what's going on? Water is being incorporated into pyroxene in point defects as a proton. This is a schematic. It's actually orthopyroxene. It's a little simpler. And there's multiple ways that you can put a proton in a pyroxene. One is you can remove a silicon, create a silicon vacancy, and have 4 hydrogens, these little blue balls, providing the charge balance. You can take a magnesium out, or any metal, cation out, create a vacancy, and have 2 hydrogens satisfy the charge deficit. You could do something trickier and take a magnesium out and put a ferric ion in and have 1 hydrogen kind of over this whole region satisfy the charge. And there's things you can do with aluminum and titanium. There's multiple mechanisms by which water as a proton can reside in a pyroxene lattice. And the beautiful thing is that these OH bonds, where the hydrogen and oxygen bonds, have vibrational frequencies that are recognizable and different when they absorb infrared radiation. And so we can see these different sites using FT infrared absorption spectroscopy through different pyroxenes. So here's the fast pyroxene that Elizabeth looked at, and this is its fingerprint. Each one of these peaks is a place where the hydrogen is in the lattice. We generally think the high wave number peaks are associated with silicon vacancies, and the lower wave number peaks are associated with metal vacancy defects. And the first thing we notice is that the other pyroxene has a very different fingerprint. So this was the slow pyroxene, this is the fast pyroxene, and the slow pyroxene is dominated by these high wave number peaks. The hydrogen's sitting in a different place in that lattice. Elizabeth also heated this up. So there's the initial spectra, and there's the spectra after heating it, or the spectra after heating it these different amounts of times and different temperatures. And you can see some of these lose their water more rapidly than others. This one doesn't very much. In fact, this one grew. So these different peaks have different diffusivities. And so Elizabeth has attempted to estimate and, well, quantify the diffusivities of these different sites by deconvolving the spectrum and then looking at what the different diffusivities would be based on concentration profiles of just those site-specific hydrogen absorbances. She did this by shooting FTIR through entire blocks of pyroxene and then looking at the entire 3-dimensional structure as opposed to cutting it. So this enables her to do a time series without destroying the crystal. And this shows for one of these, this is the high wave number peak. the center to the edge. It's zoned after dehydration. And here's the faster peak, the center of the edge. And you can see that this has lost more water, and the diffusivity is almost an order of magnitude different between the hydrogen that's in these two different sites. So that's part of it. This gives us an order of magnitude difference between these two pyroxenes, but that's not everything. Here's the diffusivities now that we've calculated. This is the bulk. These are for 5 different sites. And the sense is the same in both of these pyroxenes. This is the fast site in both. This is the slow site in both. But you can see that Jaipur is still 2 orders of magnitude faster than Kunlun. So there's something else going on, which we think is actually the composition of the pyroxenes and specifically their iron concentration. Other people have pointed this out before. So this is the full range of diffusivities and everything from synthetic diopside to here's Kunlun, here's Jaipur, and then some other pyroxenes that people have looked at. And this is plotting it against iron, increasing in this way. So synthetic diopside, essentially no iron, very slow. Kunlun has an Mg number of 98. It's not a very naturally abundant diopside. It's slow. Jaipur has an Mg number of 92. That might be more typical of mantle pyroxenes. So there seems to be an increase in the diffusivity based on iron. Iron is the bus. It's got an electron that it can let the hydrogen borrow. And hydrogen, whatever site it's in, can potentially leave the lattice by exchanging electrons with iron. We'd like to test this with natural samples, though, that have natural Mg numbers. And so here are pyroxenes from Fuego. This is the same eruption where we looked at embayments. So we know the time scale. So now we can turn around and try to calculate what the diffusivities would be in these natural pyroxenes, looking at just bulk water across the grains. Unfortunately, they break upon eruptions. These are not the most beautiful crystals, but they're what we have. And they do show zonation in water from their interior to their exterior. We can model these just like the embayments, but instead we're going to assume that we know that the decompression rate was 0.3 megapascals per second and took 10 minutes. And if that's true, then this range of pyroxenes gives us diffusivities on the order of 10 to the minus 9, 10 to the minus 10 at 1100 degrees. And if we put that on this diagram, which was at 800 degrees, you can see this is at the high end. These are the fast mechanism that, unfortunately, natural crystals seem to utilize the fast mechanism, that water is zipping through pyroxene. We confirm this a different way. This is Seguam again. Seguam is handy because it erupted both tephra, scoria, and lava at the same time. And we looked at pyroxenes in the lava and pyroxenes in the tephra. And these are based on a partition coefficient that relates the water concentration of the pyroxene to that would be in a melt. But these are clearly lower in water than these, that the lava pyroxenes have lost more water because they've taken time to cool post-eruptively on the ground. As the lava flow moved and cooled, the pyroxenes lost water. We estimated that they moved about 10 minutes from their source, and that's about how long it takes for water, 80% of the water to leave in a crystal that's about a micron, if the diffusivity is this fast at this high end. All right, so there's good news and bad news with pyroxene. The bad news is that the diffusivity that seems to be utilized in natural pyroxenes, not synthetic diopside, but natural pyroxenes, is the fast mechanism. It's moving and it's leaking. It's as fast as a melt. The way water as hydrogen is moving through the pyroxenes is as fast as a melt. So that's really bad news if we really wanted to use pyroxenes in lava flows to tell us how much water komatiites had or lips or something interesting. So that's a concern. The good news, however, is that it's a great clock. It's moving at the same rate that water's moving through a melt. And so we can use it as an ascent chronometer, and that's where we're going to go with this. I wanted to call out some other nice work that's been done along these similar lines, looking at water diffusion out of melt inclusions through olivine. So pyroxene and olivine are both nominally anhydrous minerals, but they both have these properties where they have rapid diffusion of hydrogen through their lattice, and multiple sites have been demonstrated. This is work that Marion Levoyer did with her Caltech colleagues, looking at water, mapping water in the olivine with the nanosims to see how it's leaking out of that melt inclusion. And this is nice work that Yang Chen did and his colleagues at Clermont-Ferrand, looking at inclusions of different radius losing water, and using both of these to come up with decompression rate estimates. The problem here is that they disagreed on what diffusivity to use. So olivine has issues also that we're also working on, trying to understand the different diffusivity of different hydrogen incorporation sites. Okay, so we've made it to the end. The main message that I want to leave you with is that it does not appear, despite what we might think and what's in textbooks, that the total pre-eruptive volatile concentration matters that much for eruptions, at least for common basaltic andesites. Sure, morbs don't have water, and the water doesn't leave, and morbs don't erupt explosively, and kimberlites erupt explosively and probably have a ton of water. I'm certain there's an effect. But at the order of magnitude from VEI 1 to 5 eruptions, the amount of water doesn't seem to scale with that at all. Instead, it seems to be the rate at which the water leaves. But I have a question mark. It's based on 5 data points. And so what I tried to show you is the promise in this and being able to use other clocks like water diffusion through pyroxene and olivine to understand what's going on. Because I've also not told you why decompression rate itself might vary. Why would if the decompression rate governs the style, what's governing why some magma's shooting to the surface faster than another? Is it the deep magma supply? Is it CO2 and sulfur gas? Is it the stress state of the crust? So there really isn't a way we're going to solve this problem unless we look at the clocks at the same time with the same eruptions where we're looking at them geodetically, seismically, and with gas. And this is why I actually think volcanology is kind of poised in an exciting place. We have novel time scales that geochemists have given to the field, and they're now 4D real-time imaging of volcanoes breathing and locating earthquakes well, and real-time measurement of gas, where I think we can understand what the magmas are telling us about how they get to the surface and how that drives the eruption. I want to finish with just a short story. We started with Pavlov, so I'll end with Pavlov. So again, Pavlov's in Alaska. It erupted a few months ago. The sad thing that I'm going to tell you is that despite the fact that Pavlov has erupted many times over the past decades, we have no samples of these ash-rich eruptions. Ash is ephemeral. It's gone. And it's what we need. It's well quenched. It's the explosive phase of the eruption. We need that ash. But if we'd waited till this summer to go to Pavlov, it'd be gone. It's blown away. It's mixed with the soil. So most of these go unsampled. We were lucky here in that the plume actually passed over a settlement, Nelson Lagoon. This is way down the Aleutian Peninsula. That's what Nelson Lagoon looks like. God bless these folks who live out here. And they were contacted by Christy Wallace at the Alaska Volcano Observatory via Facebook to see how they were doing, because the plume went right over them. And she kind of said, did you guys find any ash? And do you think you could collect a little bit for us? So the next day they posted this picture on Facebook. They filled up a garbage can with ash. Christy and I were like, whoa, let's get that sample. So she wrote and she said, how can we help get this sample? And they said, it's March in the Aleutians. We'd really love some produce. And so we exchanged a box of grapefruit and other goodies for a garbage can full of ash that is from this. That was the day of the eruption that had happened, the VEI 2 to 3 eruption. And we're hoping to think about this more, how we can collect these ephemeral samples with citizens, with remote collection devices, a RESCO effort, so that we have the material that came out of the vent and has the crystals in it that are telling us the story of how they ascended to the surface and erupted. Thank you.
Thank you very much. Very interesting talks. And our country has experienced the low to middle level of the volcanic eruptions every year. And this kind of work is very important to us from the scientific point of view, for the social benefit.
Absolutely.
Yeah. And do you have other questions and comments? Yes.
Yeah, very impressive talk. And I also liked your work on hydrogen diffusion and pyroxene. So my question is maybe more a comment. It's when you observe the relationship between eruption style, VEI, and the ascent rate. Mm-hmm. The ascent rate, even the smallest VEI, the ascent rate seems to be still very high. It's a few meters per second. So, and also the whole range of ascent rate is relatively small. That's kind of surprising. And so do you have any comment on that?
Okay, so recognize that these are all explosive eruptions. So even Seguam, which is, it's gone. So even Seguam, which is a VEI1, is still a violent strombolian eruption. Okay, so if we were to look at effusive eruptions, then we would probably look at much lower ascent rates. And whether this scales, I showed what looked like a log, similar range in order of magnitude in decompression rate and eruption rate. We can definitely expand that to higher discharge rate eruptions and lower discharge rate eruptions and see if this holds up. Yep. But a VEI1 is not nothing. It's a strombolian eruption and small fissure.
And do you have any other comment or the questions? Yes, please.
Hi, really excellent talk. That was really interesting work. I have a question also about the hydrogen diffusivity in pyroxenes. If hydrogen can diffuse through a pyroxene as fast as through a melt, how do you explain pyroxene-hosted melt inclusions that have significantly higher water contents than the matrix glasses that host them?
Okay, so that's a really good point. Melt inclusions have a harder time getting out. They're not just moving through the lattice at the diffusivity of pyroxene. They also require a partitioning to be favorable. So for example, a melt inclusion in olivine, sure, it will zip through the olivine, but only a small amount of it can zip at any given time because the partition coefficient is so low. So it's like having a really small wheelbarrow. So melt inclusions are still our best way, even though they're leaking. I'm certain almost every melt inclusion is leaking to some degree, but it's much less because of the partition coefficient is in your favor.
And any other questions?
Yeah, I was impressed with your relationship with the VEI and the decompression rate, but I have a feeling that something is not quite working, because once you have a given size of the eruption, you cannot have a given mass flux because you run out of magma, right? You cannot have very high mass flux rates for small eruptions because there's no magma left.
Right.
So scaling it to the VEI, I'm not so
well,
sure.
I was scaling it to the discharge rate, okay? The VEI isn't quantitative, as we know. So you scale it to the discharge rate, and yes, there's a certain circularity in this. If it's all the same conduit size, then the discharge rate governs the decompression rate.
Right, yeah.
Okay. But it doesn't have to be the same conduit size.
If you compare the same size eruption for different mass flux rates, I think that would give you...
Say that again?
The same size, so same volume, but different mass flux rates.
Oh, the same volume.
Right.
Well, I'm focusing on the discharge rate because that's what scales to the intensity of the eruption.
Right.
In the David Pyle sense.
Fine, we can talk more. You cannot have a very high column if you don't have a lot of magma, because the magma will not reach the size. So
yeah,
it's very interesting.
It's a good suggestion.
Okay, the time is over at the moment. And finally, please, the big hand to her. Yeah.
Thank you very much.
Okay, thank you very much.